All right. All right. So recall this a problem of spherical tank, building spherical tank. And it can be reformulated as so determine delta positive so that r minus 1 implies delta, r minus 1 less than delta implies 4/3 pi r cubed minus 4/3 pi less than 10^2. Okay, so this is the generic problem that we have for the next couple of minutes. Okay, rigorous study of limit. All right. So what we did at the time, okay? So what we have is you compute this one, simplify this one. Okay, right? And we take the 4/3 pi out, factor this out, and you ended up with this. Okay, and we have this r minus 1. You factor this out to binomial. And need to find a bound. Oh. For r squared plus r plus 1. Okay. What do we have for bound? Okay, let's take r between 1/2 and 3/2. So here r minus 1 less than 1/2. Okay, so in this case, r plus r plus 1, that is less than r squared plus r plus 1. So in this case, this would be 3/2 plus 3/2 plus 1. So what we have is, let's see, this is 9/4. This is 3/2. Let's see, 6/4. Okay. And so you 10, 10, 19. So take this in 5. Okay. And if we continue with this, this is less than 4/3 pi r minus 1 plus 5. Okay. So then this is less equals to, say, 20 over so if we want, or we need cube minus 4/3 pi. This is, let me just write down the last thing. It's less than 10. Then you see that r minus 1 should be, let's take this out, 3 pi over 20, right? So times. So this you can take as a as a delta. As delta. Okay. The point is that it doesn't matter if you start with 10 to the negative 2, 10 to the negative 3, or whatever the number is. Okay. Here's the get. The important is the 3 pi over 20. Okay. So so it's flexible. You can replace the 10 to negative 2 by any numbers, and you get the number delta. Okay. May replace by any positive number. Okay. And you get delta. Subsequent delta. Right? Remember that calculations? All right, so we're going to repeat that in different contexts. Okay. So basically, what we have in that computation is that if you think a function is a process with input x and output y, y is f of x, we need to have something like this. If you need that, we should try to compute an error. Say less than something here. What we need is this, and we need to find x minus something here. Minus, so that this one occurs. Okay. All right, so that's the context. Let's start with our limit now. Okay, these notations. Limit x going to a, f of x equals L. L limit means that f of x gets closer to L as x gets closer to A. Okay, but somehow you need to quantify what does it mean by gets closer. Gets closer to A. So we need to quantify. Quantify gets closer. Okay, so close or far, it's about distance, right? It's distance. And distance in math, that is absolute value. Right? So it gets closer to L, meaning that f of x minus L, it's small. we need to quantify that small. Okay? So we need to make f of x minus L, this absolute value, small. How to make it small? By making it gets closer to a, meaning small. Okay, so how small? The thing is, can be arbitrarily small. Arbitrarily small, meaning that it is less than 1, and find the x minus a approximate. 1/2, we compute this one. So any numbers, actually, you can compute this one. Okay. So let's see. Let's do some more example. Let f x equals x square. So we need to find, let's see, just a equals 1. Okay, so we know that f1 a equals f1. Oh, just change the number 2. All right, so all right, so make, the question is, make, this is L, arbitrarily small. By making x minus 2 small. Okay. Let's do some computation first. Let's check this out. X squared minus 4, right? So somehow you have to make this a x minus 2 appear from here. In this case, there is no other way than do factorizations. Okay, and we need to bound. Here's what we need. Okay, so we need to bound this and x minus 2. Find upper bound. Okay, let's let x minus 2 less than, say, 1/2. Okay, so we are working in so this is 2. 1/2 is 3 halves here. 5 halves. All right. So what we have is, this is less than x plus 2. All right, so in this case, so 4.5, basically. And you can say also, well, let's just take it 5. Okay. So this is our computations. So what we have now is that x squared minus 4 is less than, say this is still equals, it's less than 5 times x minus 2. Okay, so if we want x minus 4 arbitrarily small, sorry, okay, that's just one small, for example. Say this is less than, now I attach a symbol here, epsilon. Okay, so if epsilon equals 1, what we need here? What we need here is less than 1. Okay, so what we have is that there should be 1/5. Okay, what about epsilon equals epsilon equals 1/4? 1/4. Let's say it is the same. So now x minus 2 should be less than 1/20th, right? What about 1/10, for example? Well, that's the same thing. The computation becomes uh, clearer but tedious because that's just repeating things that we know already. Less than 1/10. So x minus 2 should be less than, let's see, 1/15. Okay, so you can take any other. So what about arbitrary epsilon? Can we work with the symbols now? All right, so let's do this one. So in general, arbitrary epsilon positive. So what we have is that here, a fifth over 5. Okay, but the thing is, don't forget, in the beginning we assume this. So this is what we call pre-assumption. So based on this assumption, we get this is less than 1/5. All right, so let's just pick the smaller one. This is 1/5. This is 1/2. Pick the smaller one. A smaller one between 1/2 and 1/5. So in this case would be 1/5, right? So if epsilon 1/4, in the end you get 1/20th. If we compare this to the pre-assumption, it should be 1/2, and we pick the smaller one, 1/20th. All right. And what if 1/10th? You again pick the smaller between 1/2 and 1/20th. Sorry, 1/15. Yeah. Or in general, because if it's arbitrary epsilon, then we have to compare this one. Due to pre-assumptions. From here, pick the smaller one. Okay, so in this case would be the minimum between and 1/2. Okay, so that's the example of what does mean by arbitrary small. Okay. So basically that's the definition of limit. Rigorous definition of limit. So we say that x going to a, f of x equals L if for every number epsilon positive, we can find delta positive such that if x minus a less than delta, then we have f of x less than epsilon. Okay. So there is a kind of long story how to get these definitions from the illustrations. Okay. So that means we're looking for any error here, error in y, you can find error of x. So that this invocation occurs. Okay, so what I mean is that okay, so I mean that error of y measurement we can determine error of x measurement. Okay, so that y qualifies y error qualifies what? Qualifies these situations. Okay, so that's the idea of an error. Okay, so how this could be so complicated? All right. Okay, so we use this definition to derive properties actually. Definition of limit. To prove properties of limit. And once we have the properties of limit, then the computation of limit use these properties, not using the proof anymore. Okay, so it's just some simple one. All right, let's see. Let's do this example. Prove that. Let's do some simpler one. You may say this is a silly example of. Let's see. What should be the limit?
3.
Yeah, 3. Let's prove it using the definition. Okay. Prove that use definition. This definition is called epsilon delta definition. Okay. Epsilon delta definitions. All right. Okay, let's do some computation first. Some, let's see, what do you call this? Some scratch, in a scratch paper. Let's see. This is our f of x. Oh, sorry. Yeah, f of x. So this is our L. This is our A. Okay. So we need to compute this one to estimate. More precisely estimate. So let's compute this one. X minus 2, right? Minus 3. Okay. This we need to find x minus 1. All right, so we should end up with x minus 1. So what, just do simplification here. So 5x minus 5, right? But here we have this 5 are same here, so you can factor this 5 out. There we go, you find the x minus 1. Okay, so you need to find it down, but you have this one. Okay, so there's 5. All right, so let's take this should be less than epsilon. Then the delta should be, let's see, x minus 1 is, let's see, epsilon over 5. Okay, so what we do for the proof. Now this is the computation part. So the proof, looks like this one. So let epsilon be positive numbers. All right. So what we need is to find delta, and what we say is that we pick delta equals here. That's our delta, epsilon over 5. Okay, so let's assume that x minus 1 is less than delta, which is epsilon over 5. Then what happens to this? We repeat these computations, but going backward. X minus, let's see, this is 5. Sorry, 3 equals 5x minus 2 minus 3 is is 5 times x minus 1. And because x minus 1 is less than epsilon over 5, from here, okay, so you see that the 5 cancels, so there's epsilon. Okay, so the idea is how we pick this delta. That's the main idea. Okay, so then that's how to we prove that the this limit for x minus 2 is actually 3. Okay. You don't have to worry if you find this as a kind of confusing. So in fact, this is in it. It is still haunting even for the third-year math students learning. We call it analysis. This generalization of calculus. Okay, so this epsilon delta thing brings quite a nightmare to students. But somehow this is calculus. So we derive the properties using this one. These are just illustrations. Okay, so let's prove the prove that now limit x one. I guess you're quite familiar with these computations because you've seen this a few times. All right, so let's do this. First thing is kind of make a little computations. So f of x, let's recognize this first. This is f of x, this is a function. This is L, supposedly. This is our A. Okay, so we need to find less than something so that x minus A less than x minus A. Okay, so let's compute this. This is just cube minus 1. Okay, and as before, you can do these factorizations. This is exactly the thing that we do with a spherical tank. A spherical tank is just an illustration of this problem. All right, so that's well, we need to bound this f of x minus L thing. But the thing is, it depends on the x. So somehow you need to bound this. Okay. In the previous example, we don't need to bound because there's already number 5. All right, so here we need to find a number which act as this 5 here, as a bound. Okay, so bound this term. All right, so as to bound this term, let's assume x minus 1 less than 1/2. You may ask also, why 1/2? Well, just a convenience. You may assume some other number. So why not 1/5? All right, so 1/5 is okay. 1/10 is okay. You can use that. Okay. So why not, for example, 2? With 2, there's a bit problem because with 2, you get some negative number. The range of x is some negative number. Okay, we want to avoid that. Okay, so this is the range. Okay, so then x squared minus x plus x plus 1, that is less than x squared. plus x. Okay, so x is less than 3 halves. This is 3 half square plus 1. So this is less than 5. We compute that already. Right? So y5. Okay, so now this is less than 5, then we can bound also by number 5. All right, so let's do the proof now. Okay, so we let epsilon be positive numbers. Okay. And what we pick is now, or pick or choose a number delta, which is the smaller one between our pre-assumptions. Our pre-assumption is this one, 1/2, and this 1/5. Okay. So let x minus 1 less than delta. Okay. So then we compute this one. Minus L is that x cubed minus 1. We factor this out, factorizations. So this is less than 5. Okay. Sorry. All right. All right. So what it means with this is that x minus 1 should be minimum of 1/2 m. Means x minus 1 is less than 1/2 and x means less than. Okay. So then take this one. So this is less than times that. Okay, so for any epsilon error, you can find the delta error. So that's the proof of this limit. Okay, questions?
Sir, I'd like to ask.
Sure, go ahead.
Can you scroll up the screen a little bit?
Yeah.
In the part that you substitute 3/2, why do you insert it 3/2, not 1/2?
Because we need to find the upper bound. So you take the largest possible x. If you need a lower bound, then you need this 1/2.
So do we always use upper bound in solving limits?
Because in this case, yes, because we need to find something like this. Just a commentary, right? Remark. Okay. In an equality, say a times x minus 1 less than epsilon, we always need upper bound for a. Okay, so the largest possible A. If smaller, then the smaller is always smaller than largest, but we need to find the largest possible for this one. You might have heard what we called, see, the worst case scenario. The largest possible. Largest possible that this is still true, still less than epsilon. Okay, so in this case, largest possible A times x minus A, so it is still less than epsilon. Okay.
Okay. Okay. Thank you, sir.
Sir, I have a question.
Yes, sure.
For the last part, it's less than 5 absolute x minus 1 less than 5 times epsilon over 5. I don't understand the less than 5 times epsilon over 5. How do you get?
All right. Here. Up to this one, is it okay?
Yes, yes. Up to
All
that
right,
point.
so let's see. Here, keep the 5, replace x minus 1 by something larger. Okay, but because we assume that x minus 1 is less than delta, which means this one, x minus 1 less than 1/2, and x minus 1 less than epsilon over 5. So we just pick this one, epsilon over 5.
The smaller one.
Uh-huh.
Oh, okay, okay, okay.
Let's do this one, one more example of doing the other things around.
I have a
Example
quick
for,
question.
yeah, sure, go ahead.
Is the method being used called precise definition of limit?
Uh-huh.
Oh, okay. Thank you, sir.
I have one more question.
Yeah,
How did you
sure.
get the first less than 5?
Less than 5.
If you scroll, hold on, wait, sorry, the stream is a little slow.
This one?
Yeah, that one. Hold on, wait, which one? The stream is a little slow. Yeah, that one.
That one? All right, this is exactly what we did in that spherical tank. That number 5, remember? Because if you compute this one, what we get is 4. This is 9, this is 6, this is 4. So this actually 19 over 4. You can keep the 19 over 4. So that means 4.4475. Okay, you can keep that one. But just to make it slightly convenient, pick a 5. That makes it true.
All right.
All right. So the difficulty here arises from the subjective nature of the problem, because you need to pick something. So you and your mates, your friends can choose different things. You may have different answer. Okay, so not exactly just one answer. It's like this one. Why do we choose a 1/2? Well, you can choose other thing: 1/3, 1/4, 1/5, 1/10. Right. Just don't make it too big. The problem. If it is too big, then it might involve a negative number. With negative number, it's slightly more complicated.
Sir, I also want to ask.
Sure.
I understand the rest, but about the assumption,
Uh-huh.
we choose a half and
Okay.
3/2. Why we choose that range of number?
So that's what I told you. You may choose. Let's do this one with a different assumption, right? So postpone this number 4. So what if we choose pre-assumption? Say, what's the number you want to be here? Your favorite number.
Is that have to be fraction, or like 25 is okay, or
No, I told you, not too big, because it's
Oh.
bigger, then it would contain negative numbers.
Negative,
Then you have
okay.
a problem with negative numbers.
how about 1/10?
Right? Okay, so if you assume this, then the range for x would be 9/10, and right?
Oh,
Okay,
I
so
see.
that's the range of 10. Then you can this one's less than x squared plus, right? So this is less than 1/100, 1/10, 1. So this is 100. So 1 plus 10 plus 100. So this is 111 over 100. Okay, so say this is 1 point, right?
I see. It's like the basic theory of absolute value, yes, sir. So
Yes,
the range would be the distance.
distance. Actually, that's distance.
Okay,
So
okay,
now
thank
with
you.
this choice, observe this thing. When you compute this one, then you use this this bound, right? Use this bound. So if you want to have this less than, all right. So let me check. Okay. So then if you like to have x minus 1, again, we just repeating this kind of computation, same computations. They should be less than 1.11 times x minus 1. So if you like to have this less than epsilon, you choose x minus 1 less than epsilon over 1.11. Right?
Okay, get it, sir.
Okay, so this is our delta in this case. So the minimum delta is actually the smaller one between your pre-assumptions, which is 1/10. The smaller one, choose the smaller one, and with this. Okay.
Okay, sir. Okay.
Now, the question is, which one's better? This choice of delta or, sorry, a bit far, this one. 1/2, 1, which is smaller? This delta, the previous one, the first one, or the second one?
The second one.
Second one is easier because this bigger. Bigger means that the, let's see, if you are from the point of view as a contractor, the more the number in x, the error of x, it would be easier for you. That's good for you. Okay, but for the owner, the smaller the epsilon would be better for her or for him. See what I mean? If you're from the side of contractor, you want as much of a leeway Well, x minus L. This is x minus 8. If you're a contractor, you want to make this as big as possible because that would make your life easier. Okay. So, but the owner wants this is small, and somehow you have to compromise. Okay, so that's the idea. So this one is better in this case because this number is bigger. Why is bigger? Because this is smaller. So to make the pre-assumptions, then, well, it's an effort actually, because you spend more effort in this, you get something bigger here. If you want an easy assumption, this 1/2, then you have a more stringent conditions, epsilon over 5, smaller. So you cannot avoid the physics of the conservation of energy. If you spend more energy in the beginning, then you spend less in the end, right? Okay, so the next example, we'll take a 5 minutes break. Okay.